Welcome everyone to our second press conference today, and it's organized in collaboration with the European Space Agency, ESA. And we will have a presentation on the new results from the Swarm satellite mission. And taking part in this press conference, we have Joseph Aschbacher, who is the Director of Earth Observation Programs at ESA, Groen Floberghagen, who is the ESA Swarm Mission Manager, Niels Olsen, who is a professor at DTU Space, the National Space Institute in Denmark, and Elko Dornbos, who is an assistant professor at Delft University of Technology in the Netherlands. And I will hand over to our speakers, who will all give their presentations, and then we will open the floor for questions from the journalists here in the room. I'm afraid scientists cannot ask questions, but we can now start the presentations. Joseph.
Okay, so thank you. So I'm having a few slides which are more generic, which are more an introduction of where we stand in the Earth observation program, and then this will be followed by detailed scientific presentations on SWARM itself by Rune and our fellow science colleagues as announced. So let me go through some of them. The ones who have, I'm just trying to move this forward, which seems not, yes. So the ones who have been at yesterday's US 2 session have probably seen some of the slides, so I apologize for those that you may have seen them already, and I hope you're still excited to listen to some of the others which are not part of yesterday's batch. So what you see here is that ESA is preparing missions, is developing satellites that are covering all the domains of the planetary observations. Planet, of course, our own planet, not planetary in the sense of the outside part, so beyond our Earth planet. So we're measuring all these parameters you see here. I'm not going through the list, but I think the list indicates that it really goes from all the elements of the land surface, the atmosphere, the oceans, the cryosphere, parameters related to climate, parameters related to agriculture, to forestry. So really a variety of different parameters which are measured by our satellite missions. The next slide shows how we do that. This is our set of satellites which are currently either under development or have been developed by ESA. Some of them for our own purposes, financed and defined by the ESA member states. Some others in cooperation with other partners meaning in particular the European Union for the Copernicus program and EUMETSAT for the meteorology missions. So there are 3 lines of our satellites which we are developing. The first one is the science missions. We call them Earth Explorers. We have launched a number of them. We are building another set of missions, and we are defining future elements of those science missions. I'm going a bit more into detail in this. The second category is Copernicus, which is a fully operational system which we are building up. And I think it is fair to say once the system is fully operational, this will be the world's best Earth observing system, which is measuring all parameters, all elements of the Earth system at a repeated frequency and really at an accuracy which is needed to better understand science, but also to better understand how our planet functions and what these interdependencies are. And there are many unknowns, as you know, which need to be monitored regularly. And on the right-hand side, you have meteorology. These are the missions we develop together with EUMETSAT, where ESA and EUMETSAT co-fund this program. We have a series of geostationary satellites. At the moment, we are flying the second generation of Meteosat. We are currently working on the third generation of Meteosat, and we also have a polar orbiting series. The first one, the currently flying, is the METOP series, and we're working on the second generation, which both of them, the geostationary and the polar orbiting missions, will fly as of 2021 onwards. What you see here is quite an interesting graph which shows how these satellites relate into publications or how they lead to publications. The various colors are representing different missions. Of course, in many cases, you have a combination of satellites, and it's not only driven by one satellite that gives you a science result. Maybe we start at the bottom of this scale, and early in the history, you have the light blue color, which is science results based on data from ERS1 and ERS2. As you know, ERS1 was launched in 1991. So ever since, a lot of publications have been produced using data from these satellites. The dark blue box or part of the chart is Envisat. As you know, Envisat was launched in 2002 and operated 10 years until 2012. And still, as you see, the majority of publications, at least until a few years ago, is still based on Envisat data. Despite the fact that the satellite ceased to exist since 2012, there are still a lot of scientific results being published there. Then you see the green bars, or the green part of the bars, which is Sentinel Missions. And this is the new data. The first Sentinel-1 has been launched in 2014. And you see that also scientists are making good use of this data and really publishing them, using this data, making scientific research and publishing them in the various conferences, journals, and so on. And this, of course, is only the beginning of the Sentinels, because we have launched today 6 satellites in the first batch of what is funded today. We have 20 Sentinels that are being built up and being launched continuously. So you will see that this green element of the bar will increase in time. And then you have the Earth Explorers. Yellow is Goche, then pink is Moss, Cryosat, and on top you have the dark red Swarm, which you will hear more about in detail in a minute. So I think this really shows there are 2 messages. One, that even if the missions have been long terminated in orbit, but there's still a lot of science that is being produced. And secondly, that operational missions like the Copernicus Sentinel missions are producing also very high return for science. I'm flipping through the next few slides relatively fast in order to give time to the swarm results. But just to show here, this is the chart of the current Earth Explorers. There are 4 of them who have been flown already. 1 of them has been deorbited, which is Goche. Then you have the 3 in orbit right now. You probably have heard about them and you know them. Swarm is the one that is being presented today in detail. And we have 4 upcoming, which are in development. Aeolus will be an extremely exciting mission coming up later this year. It's a satellite that measures wind, speed and direction in cloud-free atmosphere, not in cloudy, in cloud-free atmosphere, which is quite unusual, or quite unexpected, I would say, to measure this. The fact how you do it is you have a very strong laser beam in UV laser, which caused us also technical hiccups along the way. But this laser beam and using, of course, technology to infer wind speed will allow you to get, due to backscattering from molecules and atoms, Rayleigh and Mie backscattering, wind speed derived. Then you have EarthCare coming in the early 20s, a mission together with Japan, where Japan provides a major instrument, the CPR, and Biomass and Flex are coming early in the 22 timeframe. I mentioned metrology just to show one slide to underline the importance of satellites for society. What you see here in the yellow part of the ring is the influence or the contribution of meteorological, of METOP, which is a polar orbiting satellite for the accuracy of weather forecasts. So your daily weather forecast you get in the news and TV is to 44% based on data from the METOP satellite of ESA, which we developed for EUMETSAT, plus the satellites of NOAA, the American colleagues, plus geostationary satellites, which are surprisingly providing a relatively small contribution, which is the light blue part, and only, you see here, around 30, about 1/3, the orange circle, which is the contribution from in situ measurements, which is ground-based and air-based measurements of temperature, humidity, pressure, all the weather parameters. And if you just think back a few decades, say 2 or 3 decades in the 90s or even before, you only had in situ measurements and nothing else. And your weather forecast was only based on in situ measurements, while today with the help of satellites, of course, you have much more information, much better information, and this really contributes largely to better weather forecasts and at the end information for everyone, but also for the economy and society. Copernicus I've mentioned, just to show the chart. These are the 6 Sentinels, which I'm sure you know. But important to give also the message to you is that we are planning the future of Copernicus. So what is the next generation and how do we go from here? These are 6 candidates which we are currently studying. We have we are currently initiating phase AB1 studies, which means to define the scope, the content of these satellites based on requirements from the Commission. And they are addressing these issues which you see listed here. Carbon dioxide obviously being a main parameter stemming from the Paris Agreement, other parameters related to the Arctic, polar ice and snow topography, passive microwave imaging, and other parameters related to food security, sustainable development goals, as you know them, which are also listed here. So really to say that in Copernicus, although we are building up the world's best Earth-observing system, we are not standing still. We continue developing, and we are building new satellites. We are planning to build new satellites here listed on this graph, which are continuing these measurements and expanding the current set of observations. This is a curve which you may have seen already, which is showing the registered users downloading Sentinel data from our public data hub. It's a very impressive figure. 2014, as I mentioned, the first Sentinel was launched. Now we have, after roughly almost 4 years of having Sentinels in orbit, a very strong user community using this data. And what you see here, these 120,000 registered users, are only the users taking data from the public data hub of ESA. There are many other data hubs where these data are being retrieved, either from our member states. So we have 17 member states who have mirror sites in their countries, or we have agreements with the US. In the US, you have NASA, NOAA, and USGS who are redisseminating our data. Or in Australia, we have an agreement with Geosciences Australia. And there are commercial companies who are like Google, Amazon, SAP, who are downloading all this data, or most of this data, and redisseminating this data to their communities. So it's a multiplication of access to this data. Plus, of course, on top you have the services, the core services of Copernicus, 6 of them, who are also having their own data hubs for their own use. Some of the future challenges, where do we go? You all know what happens in the world in terms of IT revolution. You see a few of these keywords listed here. Big data, exploitation platforms, artificial intelligence, machine learning, deep learning, and so on, which are elements that come from outside the space domain. But that's a challenge we face. Of course, we use these tools, but more than that, we should really embrace it and very strongly work with it. What you also realize is that we are producing some of the world's largest amounts of data in space through Copernicus in particular, but not only. What you see here is the curve of archived Earth observation data going up pretty steep. In 2026, we have about 100 petabytes of data, which we will archive in our own data archives, plus, of course, all the other archives around the world, which are redisseminating and using these data. So really very steep increase, nothing new, but quite impressive. We are producing today 14 terabytes of data from the Sentinels alone. Sometimes I translate this into other measures. Facebook is in the news these days a lot. We are producing, for example, more data from our satellites than images and videos are uploaded on Facebook every day. So just to give you another impression of what it means to produce all this data. What you also see, certainly in the news, which you are reporting, is the amount of satellites that are being launched. Here are 2 figures which are quite impressive. 220 satellites have been launched in the last 10 years. Earth observation satellites larger than 50 kilos and not excluding meteorology. So this excludes all the small sats, Planet, and so on, which you of course have, much higher numbers. And then on the right-hand side, you see 562. So the same category, above 50 kilos, is launched in the next, not 10 years, but 5 years. So you really see how steep this goes up in terms of number of satellites being launched. Of course, many of those are coming also from private sector, and this is something that disrupts our business pretty much, and this is something which we see as a challenge where we have to work quite actively. So how do we do this in ESA? One of the first things I did when I was becoming director a bit less than 2 years ago, I reorganized the directorate. We have created a new department, which is a new unit in the directorate called Future Systems. And in the Future Systems department, we have a PHI lab, as you see here. This is a building which we built last year, which is an open space building, but open space in the sense that you really invite people from the outside to work on a project, on an activity, come with a disruptive idea, which we introduce into our activities. So how do we do that? This is the various blocks and activities that are being pursued. First of all, exploring new ideas that are not classically taken up in Earth observation today, certainly not in ESA, which include things like artificial intelligence, future architectures, non-EO technologies. Then, of course, inspiration is an important element. Hackathons, challenges are being organized, connecting people through networking activities that are being set up, framework agreements, cooperation agreements, which we are building up, especially with non-space actors. I've just signed this year a number of agreements with some of these major organizations with whom we are working. We will announce, hopefully, if the last preparations go well, a major alliance at the ELA in 2 weeks' time, which we set up with another big IT provider, not from the space domain. And INVEST, which is to create public-private partnerships with companies, industries through a program called InCubed, which we have launched last year in EXAT. So ESA is really acting as a market creator. We are buying data, but we're also helping the small set industry to come onto the market and sell their data or integrate their data in the mainstream data sources. We are not involved in the small sat build-up in building these satellites because they can do it much better without ESA. These are typically commercial companies, small companies who are building these satellites, but they do need us, and they really come all to us to see what these data can be used for, how we can integrate them into mainstream applications, Copernicus or others, how science can be done with small sats, and this is a very interesting question I would like to pursue, and how this really enters our science domain. So these are new paradigms we are exploring, not only small sats, but also high-altitude pseudo-satellites. These are platforms flying around 22 kilometers, where we want to start an initiative and prepare a funding proposal for next year's ministerial, but also mega constellations, where, of course, many satellites are taking different measurements. I mentioned artificial intelligence, something I really would like to focus on, also in the context of the PhilLab, where we use it not only for image classification, but also for segmentation, for integrating different data sources, and eventually onboard satellites to really have more intelligent acquisition planning, acquisitions, and maybe more direct connections and contacts with the users in order to download information more focused and in a more targeted way. Last, let me take this opportunity to announce that we plan to organize a large symposium called the Living Planet Symposium. Some of you know it. We had the last one in Prague 2 years ago. The next one will be in Milan in May next year, 13th to 17th of May. It typically is the largest symposium ESA is organizing at that given year. We organize it every 3 years. We have 3,000 or more than 3,000 participants usually, and this really will be a showcase opportunity to go in depth in the activities what we do. And this here shows just the program of the sessions and elements which are being displayed at the ESA booth. For those of you who have not been there yet, please visit the ESA booth downstairs, level -2, I think it is, level -2, where a number of presentations are given, how to get access to Sentinel data, how to use them, how to merge them with other data sources. So very practical hand-on sessions. So please visit the ESA booth. There is much more detailed information provided, and there are also other experts there to help you out with. Thank you very much.
So thank you very much. Good morning from the Swarm team. We are changing a little bit pace here, going from the bigger programmatic picture towards science, and in particular one of the Earth explorers, the Swarm Constellation mission. And I am flanked here by 2 of the lead scientists working with us, and we have the honor and pleasure to present new and hopefully exciting results coming from the Swarm mission. Swarm is quite like nothing else up in space. It is a mission, a free satellite constellation mission that addresses a multitude of science domains and objectives. This versatility is also going to be reflected in what we are presenting. It is a mission that is born within the Directorate of Earth Observation Programs, but it is also a mission that had at least half a leg also within the space science or solar terrestrial physics domain. So it's kind of a melting pot between Earth science and space science, solar terrestrial science. So and if you think about it, we measure the magnetic field in particular and also other parameters of the electromagnetic domain in geospace. And we are therefore able to look at processes that are Earth fixed, but also driven by the solar input. So quite frequently, we are facing the situation where the signal for one person is actually considered a noise for another. And this creates also interesting discussions and certainly also interesting synergies. To go a little bit into detail, the fact that SWARM is a multi-point, that means we have more than one satellite, and a multi-purpose Earth Explorer gives us a lot of advantage into looking into phenomena that originate not only, let's say, deep within the Earth's core. You know that the geodynamo in the outer core of the planet is responsible for a very large part of the signal that we measure in space. But then as we go upward towards the surface, we also measure parameters of the Earth mantle, of the crust, of the oceans, and also of the upper atmosphere, in fact, and indeed also the coupling between what is normally considered weather by all of us and what is considered climate and weather in space, all the way out to the magnetosphere. So it is an extremely versatile mission, and this is something that we will showcase in the few minutes ahead. So we have the pleasure here today to give you some news and updates on where we are with this mission that was launched in November 2013. And we have plans also for the future, so we hope to be able to come back also at a later stage to report even more results, obviously. So the first thing that we are going to show to you is a link to something quite fancy, actually. It is using SWARM as a kind of an oceanographic mission. The fact that the ocean water is salty, it means that it is conductive, and when it moves, for example, due to the influence of tides, this creates a tiny but in the end observable signal. It's about 1 part in 20,000 of the total magnetic field signal, and therefore hard to discover. But the interesting part of finding that signal is that it allows us to look at the integrated motion of all the seawater in the ocean due to tides. And this has implications for ocean and climate modeling. So it's something different than what you are all familiar with seeing. That is when you are on the beach somewhere and you see the water levels going up and down due to the lunar tide in particular. You see changes in the water level. This is one thing, but with SWARM we indeed measure the same thing from a magnetic perspective. And my colleague, Professor Niels Olsen, he is going to explain to you exactly what that means through a hopefully very nice and illustrative animation that we have prepared. Niels.
So this up and down of the surface of the oceans means that we have horizontal movement. We have movement of seawater in the Earth's magnetic field. This gives some electric currents in the oceans, and these currents in the oceans produce a tiny magnetic field, which is observed at swarm altitude. What you see here is this very small, very weak magnetic field produced by these ocean currents. The amplitude is about 2 nanotesla, which is 20,000 times weaker than the Earth's main field. And there are 3 reasons why we nevertheless are able to observe this field with SWARM. The first reason is that we have the very good data. We have high precision measurements from SWARM. Second is we have 3 satellites, so we are able to look at the same phenomena from different point of views. And third, we know exactly what is the period of the signal. It's given by the orbital period of the moon. And what are the what are the applications of this? Well, perhaps on the long-term run, since we are sensing not only the surface, we are sensing the whole ocean, this gives some implication on ocean modeling. But scientists already now are using these tidal signals to infer the electrical conductivity of the Earth's crust and lithosphere. And this is a completely new and unexpected application and result from the SWARM satellite.
So we will take questions, obviously, on this at the end of this talk. Item number 2 that we would like to present is linked to the objective that we have of this mission, which is to map fine details in the crust magnetic field, so the magnetic imprint in the rocks that constitute the crust of our planet. And we are happy to report that today we have determined the best ever map of the crustal magnetic field ever from space. And also we have integrated into those measurements from the SWARM satellites measurements in near-surface measurements to give us even higher resolution detail in the modeling of the magnetic field of the crust. And why is that important? Magnetic fields of the crust obviously are one key to understand the subsurface in combination with other pieces of information, for example, gravity and data from seismic measurements. And this in the end allows us, or will allow us, to determine the best ever model of the upper layer of the planet. This is a very clear ambition of the SWARM mission. We are not fully there yet, but one ingredient is already there, and another ingredient was already done a few years ago with the ESA GOCHE mission. And I'd like to emphasize that this type of a map that we are going to show to you in a second would not have been possible with a single satellite mission. It is truly a merit of the Constellation, the fact that we can combine the measurements of the lower pair of the SWARM satellites. So Niels will again explain the detail here.
Yes. So this is the most precise model of the crustal field until now. It is based on SWARM satellite data, and these SWARM satellite data give us the global view, but locally or regionally, we were able to combine SWARM satellite data with near-surface data. And this gives us some enhancement in resolution, for instance, here in Australia. We are able to see scale sizes down to 50 kilometers. Another example is Southern Africa. And this is the first model where we have a global view from the satellite in combination with regional data from near-surface observations. So what are the implications of that? Well, you have probably recognized that in the oceans there are, for instance, these magnetic stripes. And the reasons for these stripes is the following. We have material moving upward due to mantle convection. It's cooled down, and this material then conserves the direction of the ambient magnetic field at this time. So in this sense, the Earth's crust works as a giant tape recorder, recording the history of the ambient magnetic field. And we can use these stripes then to reconstruct what is the history of the ambient magnetic field.
Okay, again, we will take questions on this at the end. We are changing a little bit pace as we go outside the planet, in this case, outside the Earth, and we are looking into the magnetic fields and also the electric fields that are due to phenomena that occur in the environment around our planet. And this is because we have charged environment and electrical currents running. This constitutes also one part of the measurements, in particular of the magnetic measurements taken by the SWARM constellations. And we have one particularly new finding, which is linked to the electric currents within the polar cap. So inside, let's say, the polar cap area close to the, in this case, we will use the magnetic North Pole as the area where we illustrate this. And one long-standing debate in the scientific community has been how, let's say, the energy budget and the currents close in this area? Is this something that that happens close to the surface of the planet or really far out? And this is something that has not been possible to be observed, let's say, by observatories on ground, and we needed the swarm constellation in order to answer this question. And my colleague Elgo Doornbos will explain the detail here.
So, first of all, it's necessary to explain the concept of field-aligned currents. These are charged particles moving in and out of the region very close to the Earth, and they interact there with the Earth's upper atmosphere. So here's a figure that shows the configuration of the field-aligned currents that we already know from other satellite missions. And the scientists, they give colors to these currents so that we can better visualize them. So in the next few slides, you will see these red and blue colors that are representative of currents moving in and out of the upper atmosphere. So where do these currents come from? I've created this animation. They come from the sun. The sun normally has a magnetic field that is in the same direction as the field of the Earth, but in some cases there's an eruption on the sun, and there can be an effect that you see here called magnetic reconnection. You can see that the sun's magnetic field lines influence the Earth's magnetic field lines, and these red particles, they represent the energy coming from the sun into the Earth's magnetic field and then hitting the area very close to the Earth. So this is finally the result of the model. So this is work by colleagues of the university in Bergen. They took the swarm magnetic field measurements and subtracted the model of the Earth's core field and the crustal field that was already shown earlier. These models are getting better and better from the swarm data, but there's still some remaining signal in there. And so these colleagues took the data that represents the currents that swarm flies through. And only with satellite measurements can you measure these vertical currents. And the new model is the first full 3D representation of this entire current system. So once you have a new model, you have a very powerful tool to answer questions. And this model can answer a number of questions. And the one we are highlighting today is how these vertical currents are connected through horizontal currents, because it's basically an electrical circuit that has to close, and this happens in the ionosphere. There has been some debate in the past, mainly based on the ground magnetic observations. From ground magnetic observations, you cannot tell the difference between the picture on the right and the picture on the left, whether these currents close via horizontal currents that go directly in the auroral oval from the blue to the red, or whether there's also a current that crosses the polar cap. And now that we have the model, we can answer this question, and the answer turns out it depends. On summer, we have the answer from the model is that these currents, there are extensive currents that cross the polar cap, but in winter, this is not the case. And the reason behind this is that in the summer, the sun illuminates the polar area and basically breaks up the atmosphere into ions and electrons. So we have an increased conductivity in the polar cap in the summer that is not that large in the winter. So that is why we have this different current system. This is basically also as an introduction, as a science nugget for what comes next. And what we are going to show you now is something in the area of space weather. Space weather is something that's a hot topic these days, also because we are aware that our technical infrastructure and lives actually critically depend on technical infrastructure, which is influenced by phenomena that take place in the space around us. For most people, space weather is kind of abstract. And what we try to do with Swarm is to exemplify what actually happens, and such that people can get a visual idea about what goes on when people who are monitoring the space weather tells us that there is a storm going on in space. So we have pre-created, based on Swarm, in combination with physics-based modeling, basically, we have created a detailed and hopefully exciting, never before certainly, movie which shows how such a storm, a St. Patrick's storm in 2015, 17th of March 2015, for those who are not Irish, to explain basically how the solar wind drives heat into the upper atmosphere, or heats up the solar atmosphere, the upper atmosphere, and then how our atmosphere responds to that, and what actually goes on during such a storm. And again, Elko will explain the detail here.
Yeah, so this is a movie I created to explain this. Let me first try to pause it. Because I show a lot of information in a single movie here. You basically see two versions of the globe, and this represents the two different types of measurements. There are more measurements that SWARM makes, but the two measurements that I'm using here. On the left, you can see, maybe a bit faintly, these blue and red colors that represent the field-aligned current density. So these are directly related to the magnetic field measurements that SWARM makes. If we subtract the known core and crustal field, we basically get a representation of the magnetic field caused by these currents. On the right, you see the neutral air density at 470 kilometers, which was the altitude of the lower pair of the SWARM satellites at the time of this storm. Once I set the movie in motion, you will be able to see how SWARM C, one of the 3 SWARM satellites, flies through these areas and crosses over the poles, and how the measurements of SWARM compare to the models of these currents and the neutral densities. Well, maybe I should explain the figure on the right in a little bit more detail first. What you see here basically is the sun is basically in the lower left corner. This is the North Pole, and you can see that the density is much higher on this day side compared to the night side. This is due to the ultraviolet radiation from the sun that is absorbed in the upper atmosphere, and it basically protects us against this damaging radiation. But it also causes the upper atmosphere to expand, and that's why we see higher density at those altitudes. So that's basically the normal steady state picture. Once the currents increase because of the storm, because of the reconnection, the solar wind effect, we will see a very large distortion of this picture. And let me try to put this in motion again. So basically now you can see here on the left the SWARM satellite magnetic field measurements. There's not that much activity yet going on. On the right you can see the SWARM densities from the accelerations. And the colors, they look pretty similar. So that means that during these quiet times, the model quite nicely represents what the satellite sees. You can see here on the bottom that the interplanetary magnetic field is now starting to turn southwards. And now you can see the currents really increasing. These currents, they work the same as a current in an old-fashioned light bulb. They basically produce heat. This heat causes the atmosphere to expand, so it lifts up a column of air. And this air has to go somewhere. So basically what happens is that gravity pulls it back down, and you get these waves that at this moment in time already cover the entire globe. And you can see the interplanetary magnetic field turning northward and southward. And whenever it's turning southward, you get a new wave of energy. You get a new lifting up of the air, and it's spreading around the globe. So this, of course, affects the drag on satellites. So satellites will go down much faster during such a storm than outside these stormy periods. What's maybe even more important in terms of space weather is that also the charged particles in the upper atmosphere get moved around during such a storm, and that can cause interruptions to communications and navigation signals, for example, from navigation satellites.
And we also have 2 more items for you, nuggets for you to think about. We are now, let's say, moving to an area where we look at the coupling between what I call traditional weather, that is what all of us observe as weather, and the measurements that we obtain with the SWARM satellites in space. So it's kind of a lower atmosphere, upper atmosphere coupling phenomena. And one particular such phenomena that we have been successfully looking into is what happens when we have lightning on our planet. So basically, lightning, as we all know, are violent phenomena, and we are all very familiar with the fact that very strong electrical charge is discharged on the ground and causing people to, people get frightened and even hurt at sometimes. But at the same time, there is also energy traveling in the other direction. And there is actually significant energy traveling upward. And this is something that we have been able to successfully detect in an experimental mode on one of our instruments as a let's say, very clearly understood signal in space. And what is actually going on here is that as the part of the charge is traveling upward in the big early phase, let's say when it goes upward, and it more or less follows the magnetic field lines, the signal is somehow propagating uniformly. There is no particular phenomenon going on. But then as it hits the charged part of the Earth environment, what we call the ionosphere, there is a dispersion of the signal. It means that signal that is of high frequency, it travels faster upward than the signal that it is of lower frequency. Compare that to when you, as a kid, were throwing a little stone in the water. At least I did that. And then if you look carefully at the waves that were produced, you would actually see that the smaller waves, they were moving a little bit faster than the bigger scale things. And this is exactly the same thing here. And what actually happens then is that the magnetic signal that we can detect on board the swarm satellites it has a kind of a Whistler tone. It means that it goes from high to low frequency. So we can actually depict, that's also hence the name of the signal. We call them whistlers. This is something that hasn't been detected a lot from space, in particular not in this particular frequency range that we are talking about here. The people are studying whistlers with other type of instrumentation, but let's say for us in Swarm, we are talking about high frequency signals, but for Whistler people, it is more of a low frequency signal. But we try to show to you in an animation what this actually means. And this is what is being shown here. This is, as I said, the result from an experimental mode. There are lots of partners involved here who has been carefully looking into this type of analysis. And what we see here is a pass of two of the Swarm satellites over Africa. Early on in the mission, they were flying after one another. We see the Swarm satellites in pink and in green. And you see the detections of lightning that we are doing with the Swarm satellite. Obviously, they have not to be too far away in order to be detected. But when they are detected, we pick up this whistling signal. And this is something that we can use to successfully not only study, let's say, lightning from space, but we can also study the propagation of these waves upward and the signal structure in a way that no one has been able to do before. And the interesting thing is that with a single instrument in space, we were able to pick up something in the order of 4,000 of these events within the time frame of about 4 days. And that amounts to somewhere close to 10% of all the lightnings that occurred on the planet in this same period. So it's an exciting way to study, let's say, the coupling between the upper and the lower atmosphere, and it's a new and exciting way to use instrumentation that was actually meant to calibrate the main magnetometer on board the Swarm satellite. So this is truly exciting, and we will, as a consequence of all of this, actually change the acquisition of measurements on board the satellite in order to do much more of these type of things. So you should expect to hear more from Swarm in the area of coupling between the lower atmosphere and what we actually see and measure at the flight altitude of Swarm in the years to come. Now, we would not like to leave you without closing, let's say, with our bread and butter activity. SWARM is, after all, ESA's magnetic field mission, and we wanted to leave you with an update on what's going on with what we call the core field. So this is the magnetic field that is generated in the outer core of the planet. This is something that we all are interested to know about, because it is the shield that is protecting us from harmful radiation from space. There is a lot of discussion about how this magnetic field is evolving, and whether we or technical infrastructure will be at risk at some point. And we feel ourselves as vigilants of this business, and we would like to share with you, finally, before closing here, this last finding from the SWARM mission based on 4 years of data. And Niels will do that.
Yes. So the basic principle is we take these SWARM observations at satellite altitude between 450 kilometers. What you see here is 1 week worth of data. Now you can imagine we have 4 years, more than 4 years worth of data. This gives us the possibility to study not only the small-scale structure of the Earth's magnetic field, but also how it evolves in time. So we take these observations, then from these observations, we can infer what's the magnetic field strength at the Earth's surface. But we can also go one step further to infer what's the magnetic field at the surface of the core. That means at a depth of 3,000 kilometers, which is shown here. Obviously, the field is much more small scale because we are closer to the source, which is motion of molten iron at the top of the Earth's core. But you also can see that it's much stronger. It's about 10 times stronger. The scale in the bottom part is up to 700,000 nanotesla. The top part, it's only 70,000 nanotesla. So 10 times stronger. Now, studying these small-scale field variations, and what you see here is the first time derivative of the field. So how fast does it change? We call that the so-called secular variation. This is the secular variation at the core surface. That means at a depth of 3,000 kilometers. On the left-hand side, it's the situation before we got SWARM. On the right-hand side is what we have observed with SWARM. And in particular, we see this enormous improvement in spatial resolution. So it's not that the core field itself has changed such dramatically, not in the secular variation, but we are much better with the new data to see the fine-scale structure. In particular, we see that something is going on in the polar cap. This has been interpreted 1 year ago as a jet stream, a jet movement at the core surface. But then we also have something going on near the equator in the South Atlantic. We don't have yet an explanation for that. So this is the first time derivative of the magnetic field. But let's now look at the second time derivative. So that's the acceleration. And here it's very important that we combine all the available data from SWARM and from previous satellite missions. And here you can see how dynamic the Earth field is, how it changes often within a few months. So it's a very dynamic system. So here we are in 2002. And for instance, now we have a rather abrupt change going on. And this continues also when we launched the SWARM satellites in 2013. Okay.
So what we are seeing here is that there is a kind of a heartbeat. There is a certain cyclic period in what is going on, and we are looking for explanations for all of this. Clearly, understanding what is going on in the outer core is an ambition of the SWARM mission. This is not at all an easy task. It's certainly not a trivial task. We will not want to underestimate that. But collecting good data, high-quality data from SWARM that maps what is going on in the outer core over a sufficient time period is the best weapon in order to decipher the secrets of the outer core.
And this changing core field, this has also application, of course. We all know to use a compass, I guess. And we probably also know that the compass needle does not point towards the geographic pole. There's a mismatch. This is called declination. But most people believe that the compass needle points towards the magnetic pole. But that's not the case. What you see here today, on the right-hand side, 10 years ago in the middle, and 20 years ago on the left-hand side, is the direction of the compass needle. It's a curved path. If you follow the compass, you will eventually come to the magnetic pole, which is the red dot. But it's not a straight line. And in particular, what you also can see here is how the magnetic pole has moved in the last 20 years. And this year, we are in a very special situation, because this year, in 2018, the magnetic pole is closest to the geographic pole. It has a distance of only 390 kilometers. It moves with a speed of about 55 kilometers. 20 years ago, it was in northern Canada. It's now close to the geographic pole, and it will continue its path towards Emsa-Beagle with a speed of 55 kilometers per year.
So, this is what we had prepared for you in terms of science highlights after 4 years. We hope, as I said, to be able to invite you to more science highlights as the mission progresses. In summary, SWARM is a highly successful Earth explorer, and it continues its exploration of the Earth and also the space around the planet. This is something that we do with great pleasure, and we are continuing to invest in that because it is, as highlighted before, very important to continue develop our understanding of the Earth system. We have, as I already mentioned, a goal, very clearly understood goal, to try and understand the rapid dynamics of the outer core. But not only that, we also want to look into the upper layers and the mantle from a conductivity perspective within the years to come. So this is work in progress, hopefully. In terms of what's going on in space weather and in space climate, that's maybe a new word, we would like to understand what is going on in the background ionosphere when nothing particularly exciting is going on. In general, in space weather research, people are very much focusing on the bigger storms, and nobody really cares about fair weather. But fair weather is also important to understand what are the events that could cause and trigger the extreme events somehow. So there is a clear link there. And on top of that, we have the perfect instrumentation to look into the extreme weather events, as we have already shown you in the movie that depicted the evolution of a storm in space. And the good news after all of this is that all the 3 satellites are extremely healthy. We have plenty of resources on board. We have an extremely active user community. I would call them partner community because we are all very much entangled and working closely together. SWARM has an active community of researchers worldwide, obviously, and we are moving on together. And that's basically the plan that we plan to pursue also for the future. So with this, we conclude, and we will take happily all of your questions concerning everything that we have shown. Thank you very much.
Thank you very much for your comprehensive presentations. We'll now open the floor for questions, but just before we do, I wanted to say that the materials that were shown here are available on a USB stick that you can get from Kerry on your way out if you haven't yet. And we can now open the floor for questions from journalists. We have time for maybe 1 or 2.
Hi, Jonathan Amos from BBC News. Yeah, congratulations on that. It's fantastic. I'm just remembering the CHAMP measurement of tides, magnetic. That's just an incredible step forward. That really is. It's superb. Can I just ask about the magnetic map? We had a few years. It actually was presented at this conference first time, which was the World Digital Magnetic Anomaly Map, which incorporated huge amounts of data drawn from many countries, many research institutes, to produce this, at that stage, the most detailed magnetic map of the crustal field, what was in the rock minerals. So how does what you've presented here compare to the World Digital Anomaly Map?
So this here is a combination of swarm satellite data and the World Digital Magnetic Anomaly data. The World Digital Magnetic Anomaly data only covers the small-scale structure, whereas swarm only can see the large-scale structure. And this is the first time that we have combined both data sources in order to get all length scales.
Are there any additional questions?
Hi, Marlo Hood with AFP. You kind of hinted at it, but didn't actually address directly the question of whether you've noticed any overall weakening of the magnetic field over time, which I think is a question that some of us are interested in. And also, is there any particular significance of the joining of the magnetic pole and the geographic pole?
Yes, we see a weakening of the field. We have seen that also 5 years ago, so it's continuing. We are now trying to understand why is it weakening. And what we presented in one of our slides is this spot of field changes near the equator in the South Atlantic. And that's perhaps, we believe that this is a key to understand why we have this present decrease of the Earth's magnetic field. And the other question was related to the magnetic North Pole. We don't know why it moves, and it's also interesting to notice that we have a movement of the magnetic North Pole. We do not have a comparable movement of the magnetic South Pole. Why this is happening, we don't know.
Thank you. We have time maybe for one more question.
There was talk at the start of the mission of getting the magnetic signature of the currents, or just the tidal signature of the currents themselves. Knowing what you know now, is that a possibility? It's a very, very small signature, isn't it?
So we are able to see the currents at a specific period, which is the given by the orbital period of the moon. So this is the currents due to the tidal movement. There are also oceanic currents which are not connected to tidal movement. So we don't know exactly what is the period of that, and this is much more difficult to see that. But we are working on that.
You've just given us another challenge, Jonathan.
Thank you very much. I'm afraid we have to finish here. You are welcome to approach our speakers. There are interview rooms available on the side that you can book at the info desk here. Thank you all very much for coming. Thank you for your presentations. And our next press conference is at 1, and it's on contaminated waters, pollutants in rivers and groundwater. See you there. Bye. Thank you.